Hello, in this video let us discuss the introduction to quantum mechanics. Quantum mechanics or the modern physics is a new branch of physics which started in the year around 1900. So there are some circumstances which led to the growth of this modern physics and quantum mechanics. So let us see what is those reasons why the new physics had to be started. So there are several cases. One of such is the case of Blackbody radiation spectrum. So you know that Blackbody is an ideal concept, which means an object which can absorb all the wavelengths of light and as well as emit all the wavelengths of light. If we take an experimental blackbody and observe the wavelengths emitted by the blackbody, and also note down the intensity of the light emitted by the blackbody. So if we take such a data and show it as a graph, it will come like this. So here I have shown three set of curves at three different temperatures: 1000 Kelvin, 2000 Kelvin and 3000 Kelvin. So if we take the one set of curve, that is say for 1000 Kelvin, you see here, as you see for lower wavelength the intensity is lesser, and as I go towards higher wavelength the intensity is gradually is increasing and becomes maximum here at some wavelength, say lambda 1, and as I go towards further higher wavelengths the intensity again starts to gradually decrease. As I go towards higher wavelength, the intensity decreases. So this is the trend we observe at a particular temperature T1 equal to 1000 Kelvin. Suppose I take the black body and I heat it to a higher temperature, say 2000 Kelvin, and again I observe the intensity of the light emitted and the wavelength of the light emitted. Again I get a similar curve here, that is, for lower wavelength the intensity is lesser, then it starts to increase here and becomes maximum again, and this maximum is again at wavelength lambda 2, which is different from the wavelength lambda 1 of the previous curve, and as I go for higher wavelength the intensity gradually decreases. So this is the trend again observed for the temperature 2000 Kelvin. So similarly for further higher temperatures like 3000 Kelvin. So this is the blackbody radiation spectrum. But if we come to the classical physics, can it explain this set of curves? So if the classical physics is used to explain why this intensity is varying like this for different wavelengths, it is found that it could explain only the higher wavelength of light. That is, if I come from higher wavelength light to lower wavelength, it could explain why the intensity of light is gradually increasing here. But according to that theory, the increase in the intensity would go on like this even for lower wavelengths. Even if I go towards lower wavelength, the intensity would go on increasing like this, but in actual fact we know that it will decrease. So this decrease in the intensity of light for lower wavelengths is not explained by the classical physics. The theory that we call is the Rayleigh-Jeans law, which is based on the classical physics theory. So that is not able to explain the decrease in the intensity for lower wavelengths, and that failure is famously known as ultraviolet catastrophe. It's also called the classical physics failure. So therefore a new theory had to be proposed to explain the blackbody radiation spectrum, and this was done by Max Planck in his quantum theory. So according to Max Planck, he suggested that the probability of emission of light should decrease as you go towards higher frequency of light or as you go towards lower wavelength of light. So this means that the system must be having quantum energy levels. So this is a new concept here. In classical physics we say that the energy levels are continuous. An object can continuously increase its energy. But here Max Planck in his quantum theory suggests that the system must be having discrete or quantum energy levels to make sure that the probability of emission of light decrease as you go towards lower wavelength of light or higher frequency of light. So he also calculated what are those discrete energy levels, and it is given by E is equal to NH nu, where n is the integer 1, 2, 3 like this, and nu is the frequency of light. Here the discrete energy levels are there, and the system or the atom can go from a lower level to a higher level or from a higher to a lower level. When it goes from a higher to a lower level, it will lead to the emission of light, and that emitted light will have a frequency nu given by delta E by H. So these are the two important postulates that Max Planck makes to explain the blackbody radiation spectrum. Using such postulates, Max Planck is able to deduce an expression for the blackbody radiation spectrum, which is given by a differential equation like this: u lambda d lambda is equal to 8 by hc by lambda to the power 5 into 1 over e power of hc by lambda kt minus 1 into d lambda. So here this is the intensity of the light which is emitted between two wavelengths which are very close, given by lambda and lambda plus d lambda. Similarly, in terms of frequency also you can write the Planck's equation like this: u nu d nu is equal to 8 by h nu cube by c cube into 1 by e power of h nu kt minus 1 into d nu. So this is how the Max Planck is able to explain the blackbody radiation spectrum, according to which now it is established that the energy levels of a system are discrete in nature. Now if you take some of the phenomena like photoelectric effect, again that is not explained by the wave nature of light. Einstein makes use of the Max Planck's quantum theory, and he is able to explain the photoelectric effect, assuming that the light is traveling also in small packets of light. So that means he says that the light is moving as a particle or the packets. So there he establishes that light is having particle nature. But we already know that light is having wave nature when we come to explain the different phenomena like interference, diffraction. So thus we see that the light has two natures. One is wave nature and another is particle nature. So both of them are true. Therefore we say that light has dual nature. So some more example for particle nature of light are Compton effect, Raman effects. Now let us see the further development, that is the de Broglie's hypothesis. Now in analogy with the dual nature of light, so light is energy and it is having two nature, wave nature and particle nature. Now any particle or mass you take, it is also same as energy, but we know that this mass show usually their particle nature. So according to de Broglie, even any particle or mass should also exhibit wave nature, and those waves are called as the matter waves. So this is known as the wave nature of particles. And de Broglie also obtained an equation for what is the wavelength of such matter waves exhibited by the particles. That is given by lambda is equal to h by p, where h is the Planck's constant and p is the momentum. And frequency of such matter waves is also given by nu is equal to E by h, where E is the total energy of the particle divided by the Planck's constant. So this is known as the de Broglie's theory, which shows that the particle also has wave nature. Now here we have to note that the momentum term P is taken as mv, mass into velocity, in the classical mechanics, and also the energy term is taken as potential energy plus kinetic energy. But if we come to relativistic mechanics, that is when the velocity of the moving object is very high and comparable to the wavelength of comparable to the velocity of light, then we say it is relativistic mechanics, and during such cases we can take the momentum P as equal to gamma mv, where gamma is known as the Lorentz factor, and energy here is taken as gamma mc square, where again gamma is the Lorentz factor and m is the rest mass of the particle. So here, what are these matter waves? Are they same as sinusoidal waves? De Broglie says that these matter waves are actually wave packets which are formed by the superposition of two or more sinusoidal waves of slightly different frequency. And these wave packets represent the matter waves when the particle is moving. And the amplitude of the matter waves represent, or it is proportional to the probability density of finding the particle. So this is what the brief introduction to the quantum mechanics is.